So, following graphs show population growth for two different species. Determine the exponential equation for each graph in that form. So, remember that this is the equation that you're given on the formula sheet, right? And we've seen that unless the graph is shifted up or down, unless that happens, A is the initial amount, which in this case, for the first graph, would be positive 5, because that is the amount, the number of that species X, the population of it, at time 0. So A is the initial amount, and so for this first graph, the value of A will be positive 5. Okay. Also, we can see that the time is increasing by every year, by 1 year. You go from 0 to 1, 1 to 2, 2 to 3, 3 to 4, and so on. So P, our growth period, will be 1 year. So we can start to build this equation. We know that A is 5, and we know that P is 1. And so T over 1 is just T. So T is our one variable, it's our independent variable. We need to find out what B the base is. And to do that, you can choose any one of the other points except for the initial point where T would be 0. Can't use that. But we can use the point 1 comma 15. And B to the 1 is B, so when you divide both sides by 5, you'll get 3 on the left side. So B equals 3, and now we can write our equation. Y equals A, which is 5 times 3 to the power T. And you could check that with your calculator. For example, when T is 2, 3 squared is 9 times 5 does equal 45, so we get the right Y value for that point. When T is 3, 3 cubed is 27, and 5 times 27 does equal 135, so it worked for that point. And when T is 4, 3 to the 4th is 81, 5 times 81 does equal 405, which is the right Y value for the last point. So all those points check, our equation is correct. So for the second graph, again, we're using the general form that we're given on the formula sheet. In this case here, our initial amount is 25. That's our A value. And once again, we're given in the graph that the time in years is going up by 1 once again. So that is our P value, 1. And T divided by 1 is T, so we'll have 25 times B to the power T. And once again, if we use any point, it's easiest to use that first point, the point 1 comma 50. So that means that Y is 50 when T is 1. In this case here, if you divide both sides by 25, our B value will be 2. And our equation would be Y equals 25 times 2 to the power T. Okay? And we can check that as well in our calculator. When T is 2, 2 squared is 4. 4 times 25 is 100. When T is 3, 2 cubed is 8. 8 times 25 is 200. When T is 4, 2 to the 4th is 16, and 25 times 16 does equal 400. That's our last point. Okay, so they all check. We know our equation is correct. Instead of giving a graph, sometimes you'll give in a scenario. It says penicillin decays exponentially in the human body. So because it's decaying, that is a decrease function Remember, that means our base has to be between 0 and 1. It's got to be a decimal. If it's an increasing function like the last two, that means the base is greater than 1, and it was. But this is a decreasing function. Suppose a patient receives a 300 milligram dose of penicillin to combat strep throat. About 180 milligrams will remain in the patient's body after 1 day. Write an equation for the relationship between the number of days D since the patient took the penicillin and the amount of medicine M remaining in the patient's body. So we'll start with that general equation again, right? Now in this case here, the initial amount is 300 milligrams, so that's our A value. And in this case here, like, we're not given a graph, so we're not told what the number is after every so often. In this case, it would be days, so we'll just go with 1 day. And in this case, 1 day has gone by, and we'll say our growth period is how much is going to be left after 1 day, right? And the reason we're using 1 on the top is because we're told about 180 milligrams remains in the patient's body after 1 day. So that's the amount at the end. 180 will equal 300 times B. And to find out what B is, we divide both sides by 300. 180 divided by 300 is 0.6. So there's our B value. And instead of using the equations y and t, let's use the variables that we have here, where m, the amount of medicine remaining, can be found by taking the initial amount of 300 times our b value, which we found to be 0.6, to the power d, which is the number of days. So there's an equation for that scenario. Right? Okay, so now let's go on to solving exponential equations. So we're going to determine the solution of an exponential equation in which the bases are powers of one another. We'll look at problems involving exponential growth or decay, and then we'll also solve problems involving exponential equations, involving the application of exponential equations to loans, mortgages, and investments. So an exponential equation is an equation that has a variable as the exponent. Exponential equations or expressions can be written in different ways. It is often useful to rewrite an exponential equation using a different base than one that is given. This is helpful when solving exponential equations because the exponents of exponential expressions with the same base can be equated to each other. For example, if you have this exponential equation that you want to solve, this can be done by making the bases the same. Right now the bases are 4 and 8. Those can both be changed to bases of 2. 4 is 2 squared, 8 is 2 cubed. So that is done. And then when you have one exponent raised to another, we know you multiply the exponents. That gives us the next line by multiplying the exponents. And now we are told that the two sides are equal. We started with that statement at the beginning. The two sides are equal. The key is when we're trying to find the value or values of the variable that makes them equal. But we are told that they are equal. And so if you have an expression that is equal, or two expressions that are equal to each other, in this case, two exponential expressions that are equal to each other, if the bases are the same, which they are now, then the other parts must also be equal. If the bases are equal, then the other parts, the exponents, must also be equal. So we're not really doing a mathematical operation to get rid of the bases. We're just saying that if the two sides are equal, and they are, if one part is equal, meaning the bases, then the other parts must be equal as well, meaning the exponents. So that's where we get the fact that 4x equals 3x plus 3. It's the exponents from the previous step. And then you can solve for x. So that's how we're going to solve these exponential equations. And so all the ones that we're going to do today, if we're going to do them algebraically, we can make the bases the same. You can solve them using the graphing calculator, which we can use if we cannot make the bases the same. But in those scenarios, we're going to have to estimate what the answers will be because they will be irrational, which means you would have to round them. When we get into the next chapter on logarithms, we'll see how we can algebraically solve any exponential equations. The bases don't have to be the same, and you can use logarithms to do that. So let's first look at rewriting expressions with different powers. We want to write 27 with a base of 3. Well, 27 is 3 cubed. They are equivalent. It's just that we changed it from 27 to the 1, change it to 3 to the power 3. 9 squared written with a base of 3. Well, 9 is 3 squared, and because the 9 was squared, so must the 3 squared be. And again, when you have one exponent raised to another, you multiply the exponents and the base stays the same. And that is correct. 9 squared is 81. 3 to the 4th is also 81. So you can check these to make sure. Which we will definitely do for this last one. It's a little more complicated. We want to write it with a base of 3. 27 is 3 cubed. And that is raised to the power 1/3 because the 27 was. Now, we have the cube root of 81 squared. 81 is 3 to the 4th. And the cube root squared means power 2/3. The denominator of a rational exponent tells you what the root is. The root tells you what the denominator of the rational exponent is. Because it's a root 3, or cube root I should say, that means the denominator is 3. And because it's raised to the power 2, that's the numerator. When you have one exponent raised to another, you multiply the exponents. 3 times 1/3 is 1. And when you multiply 4 times 2/3, it's 4 over 1 times 2 over 3. That gives you 8/3. And now, when you're multiplying powers with the same base, you add the exponents and keep the base the same. So because we have to add 1 to 8/3, we need a common denominator. That 1 would be 3/3 plus 8/3. 3/3 plus 8/3, which is 11/3. So there's our final answer. And in this case, we'll use our calculator to check, to make sure that the answer we got at the end is equivalent to what we started with. We started with 27 to the power 1/3 multiplied by the cube root. Whoops. Bless you. Multiplied by the cube root of 81 squared. Now, it doesn't matter if the squared is under the radical, just on the 81, or the whole thing. It's the same thing. But when you work that out on the calculator, that's the irrational number you get. Well, that should be the same as what we got as an answer, 3 to the power 11/3. And it is. So that tells us that our answer is equivalent to what we started with. The difference is that we've written it with a base of 3. And it's much simpler than what we started with as well. Okay, so for this next one, we want to write them with bases of 2. So 4 is 2 squared, and because the 4 was cubed, the 2 squared would be as well. And when you have one exponent raised to another, you multiply the exponents and keep the base the same. So we could check this one if we wanted to. 4 to the power 3 is 64, and 2 to the power 6 is also 64. So our simplified answer is equal to what we started with. 1/8 would be 1/2 cubed, or 2 to the negative 3. We're asked to write them with powers with a base of 2. And the last one, 8 is 2 cubed. That's raised to the power 2/3. 16 is 2 to the 4th. And the 16 is under the radical. That's a square root of 16 cubed, which is power 3/2. Remember, the denominator of a rational exponent tells you what the root is. It's a square root, so you need a 2 on the bottom. It's raised to the power 3, so the 3 is on top. Again, when you have one exponent raised to another, you multiply the exponents. 3 over 1 times 2 over 3. The 3's will cancel, and you'll get 2 squared. For the second factor, when you multiply 4 over 1 times 3 over 2, you'll get 12 over 2, which is 6. And now when we add 6 and 2 together, we'll get 2 to the 8th. Again, we could check this on our calculator. Take the original expression, 8 to the power 2 over 3 times the square root of 16 cubed is that value. And if we check our final answer of 2 to the 8th, it has the same value. So our answer is equivalent to what we started with. It is correct. We've expressed that expression with a base 2. Okay, so now we can look at solving some exponential equations. Remember, if we can make the bases the same, then the exponents are equal as well. And in this case, we can actually express both sides with a base of 4, because 4 cubed is 64. 4 times 4 is 16, times 4 is 64. So on the right side, we would just want to multiply the exponents, because that's what you do when you have one exponent raised to another. We have expressed both sides with a base of 4, so they are equal. Now what, Tyson? Take your earbuds out and put your phone away, please. We have expressed both sides with the same base. The expressions are equal. If the bases are equal, the other parts are equal as well. The exponents are equal. So we'll subtract the x from both sides, which will leave us with 2x on the right equaling 2 on the left. And then when we divide both sides by 2, we'll get x equal 1. Which we can check. In our original expression, when x is 1, the left side will be 4 to the power 1 plus 2, or 4 to the power 3, which is 64. And on the right side, 64 to the power 1 equals 64. So it checks. You get the same thing on both sides. Now for the next one, you could express 8 with a base of 4, but you'd have to use a rational exponent to do that. Easier to express both sides with a base of 2. And again, when you have one exponent raised to another, you multiply the exponents. And so now we've expressed both sides as a single power with the same base of 2. The two expressions are equal to each other. If one part, the bases are equal, then the other part, the exponents, must also be equal. So now we will solve for x. I'll subtract the 4x from both sides. I'll add the 9 to both sides, and then divide by 2. So there's our answer. X equals 9 halves, which is 4.5. We can check that in our calculator. 4 to the power of 2 times 4.5 is that value. 8 to the power 2 times 4.5, take away 3, same number. It checks. Our answer works. Okay. So this one says solve, and we'll check our answers using graphing technology. We'll actually graph them and to confirm our answers. But it starts with first algebraically determining our solutions by making the bases the same. 4 is 2 squared, so we can express both sides with a base of 2. Before we get rid of the bases and just work with the exponents, we need to write the right side as a single power by multiplying out the exponents. So 4x will equal 2x plus 6. When you subtract the 2x from both sides, you'll get 2x on the left equaling 6 on the right. So x equals 3 is our answer. To check this on the graphing calculator, in y1 we'll put the left side, 2 to the power 4x. In y2 we'll put the right side, 4 to the power x plus 3. The solution will be the point of intersection to these two graphs. The x value at the point of intersection, which we got an answer of 3. Zoom 6 to set our windows to their standard settings. And if we try and find our point of intersection, second function trace, number 5 for intersect, enter, enter, enter. Even though we can't see it, it still gives it to us and confirms that our answer is x equals 3. So you don't have to change the windows if you're looking for the x value. Right? So for question B, we could express both sides with a base of 9, but the 27 would have to be 9 to a rational exponent. It'll be easier to express them both as a power of 3. 9 is 3 squared. 27 is 3 cubed. So we'll get 3 to the 8x equaling 3 to the 3x minus 3. So now we've got both sides expressed as a single power with the same base, so the exponents will also be equal. So that'll give us 5x equals negative 3 and x equals negative 3/5, or negative 0.6, which we can check using our calculator. Our first equation will be 9 to the power 4x. Our second equation is 27 to the power x minus 1. We'll graph them. And our point of intersection should be at negative 0.6. And it is. So you can check them algebraically by plugging the number back into the two equations and making sure you get the same value on both sides. Or you can check them graphically. Make sure that your solution is the point of intersection between the two graphs. Some, though, need to be solved by graphing because we can't make the bases the same. Once again, when we get into logarithms next chapter, we will be able to solve these algebraically. But we're not there yet, so we have to do them graphically. And that means you're going to estimate what your answers are. You're going to have to round them. And so if this was a question on the diploma exam, you'd be told how many places to round it to. But we're not, so we will just round to the nearest, let's say, hundredth. 2 to the power 2x is our first equation. And that must equal 3 to the power x minus 1. Again, we graph and find our point of intersection. It looks like it's negative 3.8. But just to confirm, let's quit out of that and bring our x value back. So yes, if we round to the nearest hundredth, it'll be negative 3.82. Okay? For that next one, again, doesn't matter how complicated it is, we can use our graphing calculator. So y1 will be the left side, 4 to the power 2x minus 1. Our second equation is 6 to the power of x plus 2. Whoops. And then the minus 1 is on the end. Second function traced, number 5 for intersect, enter, enter, enter. Looks like 1.99945 it looks like, but let's quit out of there and bring that x value. So yeah, so we'd have to round that to -2. But it's an approximation, so we use those squiggly brackets. Christina plans to buy a car. She has saved $5,000. The car she wants costs $5,900. How long will she have to invest her money in a term deposit that pays 6.12% per year, but it's compounded quarterly before she has enough to buy her car? So using the formula that is on the formula sheet, again, the one that we have been using, it's y equals a times b to the power t over p. So we want to know how long she would have to put the money in there so that she can buy her car. So we want to find out what t is in this case. That's what we're trying to find. We do know that the amount that she has at the end needs to be $5,900. We know that the initial amount that she puts into her term deposit is $5,000. So that is our A value. To find our B value, here's what we have to do. Her interest rate is 6.12% per year, per annum, but it's compounded quarterly, which is 4 times a year. That's what that means, or every 3 months. Okay, and in fact, that will be our p-value. Our growth period will be 3 months, because that is how often the interest is calculated. Once again, where that comes from is the fact that it's compounded quarterly, which means 4 times a year. So if you go 12 months divided by 4 times a year, you get 3 months. That's how often it is calculated. That is our growth period. Now, to find out what B is, we have to calculate what the quarterly interest rate is. You also have to remember that once we calculate the quarterly interest rate, we're going to add it to 1, because you're going to have 100% of the amount that you put in there plus the quarterly interest rate more. And so the 1 represents the 100%. Your money is growing, so you're going to have 100% of what you had before plus whatever interest you get from the quarterly interest rate. So to calculate the quarterly interest rate, the annual rate is 6.12%, which we always change to a decimal, and that needs to be divided by 4 because it's compounded quarterly, 4 times a year. So we'll use our calculator to help us do this. If we do the 0.0612, which is our annual rate, divide by 4 to get our quarterly rate, it's 0.0153, and then we have to add 1 to that. It'll be 1.0153. Again, the 1 represents 100% plus 0.0153 more, which is where the interest comes in. So now we can set up our equation. The amount at the end, y, is 5,900, and that equals a, the initial amount of 5,000, times b, our base, which is 1.0153 to the power t over 3. And we need to solve for t, which we cannot do algebraically. We are going to have to use our graphing calculator. Once again, when we look at logarithms in Chapter 8, we will be able to do this algebraically. Now, if you wanted, you could simplify a little bit by dividing both sides by the 5,000, but you don't even have to do that. We can just put the equations into our calculator. Equation 1 will be the left side, which will be y equals 5,900. Equation 2 will be the right side, which is our 5,000, bracket 1.0153 to the power x over 3. Now we are going to have to change our windows because that first equation is y equals 5,900. So we can manually go in there and change our windows, or you can use Zoom Fit. For most calculators, when you hit Zoom, Fit is number 0 in the list, and that's where it is on my calculator. You may have to scroll down to make sure that it is at 0 where it says Zoom Fit. When you choose that, the calculator chooses the windows for you. But you need to be able to see the x-intercept. In this case here, the x-intercept is beyond our x-max. So we're going to have to change it. In the previous example, even though we couldn't see the x-intercept, it was within the windows that we had on our calculator. In this case, it's not. If you try and find your intersect here, you're going to get an error. Yeah, because your x-max isn't big enough. It doesn't contain your solution. In the other ones, it did. So that's fine. We'll just have to change our x-max to something bigger. And we don't know what it should be. Let's let x equal 100, our x-max. Again, we just have to be able to see, or our x-max has to include the point of intersection, which in this case, we'll also be able to see it. So there we go. Now we can see the point of intersection. Second function trace, number 5 for intersect, enter, enter, enter. So it's 32.7. Which no matter what, you'd have to round up. Even if it was 32.2, if you rounded it down to 32, Christina would not have the $5,900 that she needs. So no matter what, you always will round these ones up to 33 months. And the reason it's months is because that is the unit that P is. P was in months, so T must be in months as well. So that's how many months, but then it says, how long will she have to invest her money before she has enough to buy the car? So we can write it in months, or we could also write it in years by dividing by 12. It's approximately every, well, again, you'd have to round this up because it happens quarterly. So you'd have to round that to 2.75. So quarterly means it has to be to the nearest 0.05, which in this case would be 0.75. So approximately well, actually it's not approximately, it equals, it's not approximate, it's 2.75 years. Okay? So on the next page, determine how long $1,000 needs to be invested in an account that earns 8.3%, and the interest rate is always annually. but this time it's compounded semi-annually before it increases to a value of 1490. So again, using the formula that's on the formula sheet, y, the amount at the end, is going to be 1490. A, the initial amount, is 1,000. T is what we're looking for. P, the growth period, is every 6 months. Because it's compounded semi-annually, the interest rate is calculated twice a year, or every 6 months. To find B, again, it's going to have 1 plus something. That 1 represents 100% of the money. As the money's growing, the interest is calculated every 6 months. So every 6 months, you're going to have 100% of what you had, plus the extra amount that you're earning in interest. And in this case here, it's found by taking the annual rate of 0.083 and dividing it by 2, because the interest is calculated twice a year, semi-annually. So to our calculator, 0.083 divided by 2 is 0.0415, which we have to add 1 to get 1.0415. So now we can set up our equation. The amount at the end is 1490. That equals the amount at the beginning, which is 1,000. Our base is 1.0415. Right? That's always our growth rate, to the power t over 6. The growth period is every 6 months. And in this case, we could make it a little bit simpler by dividing both sides by 1,000. You get 1.49 equaling 1.0415 to the power t over 6. Now, you don't have to divide both sides by 1,000. It's just simple to do. So our first equation will be our 1.49. Our second equation will be 1.0415 to the power x over 6. So if I go zoom fit, I need to see the point of intersection, which I do. Second function trace, number 5 for intersect, enter, enter, enter. Looks like it's around 58.8, but to make sure, quit out of there and bring back the x value, so yes. Now again, you're going to have to round this up to 59 months. Okay, so t would be 59 months, which actually we'd have to even round up to 60, because it's every 6 months or twice a year. So the interest won't be calculated at the end of 59 months. It'll actually be calculated at 60 months, because that's the end of the 5th year. And if you take that 60, well, actually even the 59 if you want, and divide by 12, I'm sorry, I said 6 years, it's 5 years. 5 times 12 is 60. So after 5 years, there'll be a little more than 1,490. But if you back it up to 4.5 years, it would be less than 1,490. The value of a car depreciates by 14.5% per year. If a car has an original purchase price of $68,500, what is the value after 8 years? So again, we're using this formula. Y is the amount at the end, which is what we're trying to find in this case. A is the initial amount, which is 68,500. B is our growth rate, okay? It's depreciating by 14.5%, which means to find out how much is remaining, we would take 100% or 1 and subtract the 14.5%, or take 1 and subtract 0.145, which is is it 855? 1 minus 0.145, yeah, 0.855. You see, your growth rate is always what percentage is going to be there. Not what's being taken off, but what's going to be there. So you have to do that extra calculation. Okay? And P, our growth period, will be every 1 year. And in this case, our time is 8 years. It's depreciating by 14.5% every year. That's why the growth period P is every 1 year. So we want to find out what Y is. What is the value of the car after 8 years? Where A, the initial amount, is 68,500. We've determined that our growth rate, it's depreciating. It's a decreasing function, so our base B is between 0 and 1. In this case, it's 0.855 to the power 8 over 1, or to the power 8. So we just have to put this into our calculator. 68,500 times 0.855 to the power 8. And so there's the value of that car after 8 years, 19,562.28. There's the value of that car. Okay? So, for homework, for practice, you can do on page 364, number 2 through 5 and 7. So I will post those solutions on Google Classroom so you can check your answers. Remember that we're having a quiz tomorrow on chapter 7 because we're now done this chapter. So that'll be tomorrow. Okay? Sure.